Okay, let's do a calculation involving something more complicated, a 3 by 3 matrix example. Yeah, let's go. So let's take a look at the following 3 by 3 matrix. P will be the matrix, let's see, I've got a nice one cooked up here. 3, 0, 0, 1, 2, 0, and 0, 1, 1. All right. So this is a 3 by 3 matrix. And what we're going to do first is write down its characteristic polynomial. So the characteristic polynomial of P is, by definition, the determinant of P minus lambda times the identity. Okay? That means we just take P and subtract off lambda from each of the diagonal entries. So we're talking about the determinant of the 3 by 3 matrix, lambda minus 3, 0, 0, 1, 2 minus lambda, 0, 0, 1, and then 1 minus lambda. Okay? Now, to compute the determinant of this, what I'm going to do is cofactor expansion along the first row. Why the first row? It's because... wait, something is bugging me here. Oh, are you all yelling at me through the screen right now? You really should be, because I messed up. And if I had any shame, I would apologize, but not sorry. You see that? Lambda minus 3? Of course, it should be 3 minus lambda. You subtract lambda from the diagonal entries, okay? So don't do this. This is exactly the kind of thing you do, like on an exam or something like that. So this is a good warning to you. Don't do that. In fact, what you want to be writing there, of course, is 3 minus lambda. I did it on purpose. Yeah, I did it on purpose. Okay, this is all to yeah, did it on purpose. So if we cofactor expand along the first row, okay, what we obtain is 3 minus lambda times the determinant of the 2 by 2 matrix that we get by deleting the first row and the first column. That is to say, this 2 by 2 matrix right here. That's 2 minus lambda, 0, 1, 1 minus lambda. And we know how to take the determinant of 2 by 2s. That's easy. That's the product of the diagonal entries minus the product of the off-diagonal entries. So we get 3 minus lambda times 2 minus lambda times 1 minus lambda minus 0. So I'm not going to bother to write that. In other words, this is my characteristic polynomial. And quite beautifully, it's fully factored. What allowed for that to happen? What allowed for that to happen is the fact that this matrix here is what's called a lower triangular matrix. What does that mean? That means that the entries, the only non-zero entries, either lie on the diagonal or below the diagonal. That's what we mean by a lower triangular matrix. There's also the notion of an upper triangular matrix where all the non-zero entries are either on the diagonal or above it, okay? But there is a fact that I'm happy to state for you and that you can use in your life. The eigenvalues of an upper triangular or lower triangular matrix, sometimes collectively called a triangular matrix, lie on the diagonal. The proof of this is easy. It's just cofactor expansion. In the case of an upper triangular matrix, you do repeated cofactor expansion along the first column. And in the case of a lower triangular matrix, as in this P that I've got here, you do cofactor expansion along the first row. And if you do that, and you compute the determinant of P minus lambda I, you're going to end up with the fully factored characteristic polynomial, and the roots of that fully factored characteristic polynomial are going to be quite obviously the entries that lie on the diagonal. So do you see here? We've got the 3, the 2, and the 1 there. Those are exactly the roots of this characteristic polynomial. That's not a coincidence, okay? But yes, indeed, the eigenvalues we see here are lambda equal to 3, 2, and 1. And what we want to do is compute eigenvectors associated with each of these. Okay, so let's start with lambda equal to 3. So what I'm going to do is solve the equation p minus 3 times the identity times v equals 0. What is p minus 3 times the identity? Well, I can just look here and plug in lambda equal to 3. And what I get is the, and I'm going to make an augmented matrix as usual. I'm going to write, let's see, I'm going to have 0, 0, 0, and then 0 for the augmented first entry of the 0 vector. Then I'm going to have 1, minus 1, 0, 0. And finally, I'll have 0, 1, negative 2, 0. Okay, that's my augmented matrix. Now, that we already have a 0 row in that first row there, so that's really nice. Okay, what is this? What is this thing? The system? What does it sort of boil off to? If we think of V, of course, as being V1, V2, V3. So if we think of V, maybe I'll write this up here. If I think of V as having entries V1, V2, and V3, then this matrix here represents the system V1 minus V2 equals 0, and V2 minus 2V3 equals 0. What this suggests to me is that I can write V1 and V3 quite easily in terms of V2. So that's what I'm going to do. I'm going to write V1 and V3 in terms of V2. So this is equivalent to saying, for example, that V1 is simply V2. Okay, that's cool. And then the second equation is telling me that V3, if I subtract V2 and divide by negative 2, is I get 1/2 V2, I believe. So then V, my eigenvector, can be written, sure, it's V1, V2, V3, but V1 is V2 by this equation, yeah? And V2 is V2, and V3 is 1/2 V2. I wish I had made this longer, like this, yeah? And now I can just pick an arbitrary value for V2. V2 is sometimes called a free variable in this system. So let's choose a V2, which is going to get rid of that 1/2, which I hate. So choose V2 to be 2. Then V, my eigenvector with eigenvalue 3, is 2, 2, 1. And you can check that if you do P times V, you're going to get 3 times V. Okay? Let's do lambda equal to 2 now. Okay? We have to solve P minus 3i times V equals 0. Or sorry, 2i. That's the whole point. The eigenvalue has changed now to 2. So what is the augmented matrix here? So it's what I get by sticking 2 in for lambda into this matrix here, and then adding a column of zeros. So I get 1, 0, 0, 1, 0, 0, and adding a column of zeros. And then finally 0, 1, negative 1, I believe. Yeah? Now, of course, what I can do is maybe add negative 1 times row 1 to row 2 to kill that second row. And I'm not too concerned, but this is what I end up with. Now, thinking kind of in the way that I did before, what does that first row tell me? That first row tells me that V1 must be 0. That's my constraint. V1 has to be 0. What about V2? Well, the second row doesn't tell me anything. It's vacuous. The third row tells me that V2 minus V3 is equal to 0, right? So in particular, I can write V2 in terms of V3. This is equivalent to. So if I think about V as being V1, V2, V3, V1 must be 0. That's what that first equation tells me. V1 is 0. V2 can be itself. And V3, I can see from this equation, must be equal to V2. So I get this equation. And I can let V2 be anything non-zero here. So let V2 be, I don't know, 1. If I do that, then I get my eigenvector being V equals 0, 1, 1. And that's an eigenvector with eigenvalue 2. Okay, one more calculation. Let's do lambda equals 1. And we're going to solve P minus I times V is equal to 0. So if I plug in 1 here into this, the augmented matrix that I get, maybe I'll put it down here, is 2, 1, 0, and then what are the off diagonals? 1, 1. Like this. 0, 0. Oh, and this should be an augmented matrix, no? Am I doing this right? 1. I think so. Okay. So I can use the first row to kill the 1 in the second row. Kill that one right there. So if I do that, I get 2, 0, 0, 0. I get 0, 1, 0, 0, and then 0, 1, 0, 0. And you can see now I can kill the third row by just adding -1 row 2 to row 3. And I believe I get this. And what this is saying is that this implies that 2v1 is equal to 0. That's what the first row is saying. And the second row is saying that v2 is 0. Those are the only constraints. So of course what this says is that v1 must be 0 and v2 must be 0. v3 can be whatever it wants to be. It's a free variable. So what we can do is make an eigenvector v be, for example, 0, 0, 1. This is an eigenvector with eigenvalue 3. So to summarize, what we've just done, and I'll end this this video momentarily, we found 3 vectors. These 3 vectors are eigenvalues. No, I'm sorry, eigenvectors. But they have different eigenvalues. The eigenvalue of the first vector is 3. The eigenvalue of the second vector is 2. And finally, the eigenvalue of the first vector is 1. Not every vector is an eigenvector. You have to follow this procedure to find them, okay? But there are infinitely many eigenvectors for any particular eigenvalue. Okay, that's enough for this one. In the next set of videos, we'll talk about how to use these to solve some linear systems. Okay, see you in the next one.